We'll pick up where we left off last time, talking about the Tidyverse, actually just beginning to talk about the Tidyverse. But before we do that, I want to mention one thing that I got wrong last time and expressed some uncertainty about what was happening. I had just forgotten that when you do 1:k for some integer k, it produces integer values. So when we summed the first k positive integers using this sort of operation, what you get is an integer. And when we applied the formula n times n plus 1 over 2, what we got was a numeric value or a floating point. Even though the answer turns out to be an integer, it's different from the point of view of the underlying types of these objects. And so the identical function in R, which, as we said, checks whether the R objects are actually exactly the same as each other, it will say they're different even though the values are the same, because it sees that the types are different. So that's what was happening there. And that's the difference between checking that all of the numbers are equal to each other, entry by entry in the two vectors, and using the identical function. Okay, so the main topic today is something called the Tidyverse. And the Tidyverse is a popular suite of packages that are designed to be used together, and their R packages are very much integrated with the R universe. And the name here warrants some explanation up front. It's not saying that this is a tidy set of packages that provides a particularly convenient working environment, although that's also true. The name comes from the word tidy in the phrase tidy data or tidy format that you might put data in. So we've talked about this a little bit already, but I want to make sure that we lean into this a little bit. Before we talk about tidy data, though, I just want to establish some context, because it is a fairly unusual situation that you have a set of packages in a language that comes to sort of dominate the use of that language. But that's what's happened with R. So these packages were developed by a very prominent, probably the most prominent user in the R community, called Hadley Wickham. About 15 years ago, the first package in the Tidyverse was created, and they've become very popular to the point where you often see people considering them the standard way to use R. So people won't make histograms with the hist function that we've seen. They'll use the histogram functionality built into the Tidyverse package, built into ggplot2, which is the graphing package in the Tidyverse. And it looks quite different. And that's going to be true for many other operations. So that's sort of how you want to think of this. It is kind of supplanting some of the base R functionality, but it's going to do it in a nicer way, as we'll see. And you shouldn't feel that I'm sort of taking you far afield here with this kind of niche package. This is, in fact, the way people do things nowadays, by and large. Okay, so as a review, we'll define what tidy data is again. So we say that a data table is in tidy format if each row represents one observation and each column represents a different variable available for each of those observations. So the murders data frame that we've been looking at is in tidy format. So each row is an observation, namely a state, and the columns correspond to different pieces of data available, abbreviation or population, etc. So it might seem like when you see this example, what other format could data be in besides tidy? And here's an example of another way to present some data. This is a tidy data set. It's got each row corresponds to a particular year and country, and we're making a single observation of a fertility rate. But you could put this data together in a different way by making the year the column header. So this would look something like this. So we could have 1960, 1961, and 1962 as our three columns, and record the entries here for the fertility rate. So this is not in tidy format because each row doesn't correspond to three observations. Each row doesn't correspond to a single observation. It corresponds to three observations, the fertility rates in these three different years. So we bring this up in particular because it's important to reshape your data into tidy format if you're going to use it in the Tidyverse package, because they're very much designed to handle data in this consistent format. A lot of what we're going to see for how clean and organized you're able to create your code for data transformations, it comes from making consistent assumptions about how the data is structured. And so if it's not structured that way, you'll need to get it that way at the beginning. And then after that, you'll be able to use the full advantages of the Tidyverse packages. Right. So you'll see as we go the advantages of doing this and how it makes the code really clean. Okay, so I want to start by giving you a multiple choice question. This is our first question of the day. So if we pull up the CO2 data set, we've seen it before, it's a built-in data set, it looks like this. Then what can we say about this data frame? Is it tidy data because it has 1 year for each row? Is it not tidy data because we need at least one column with a character vector in order for the data frame to count as tidy? Is it not tidy because it's a matrix instead of a data frame? Or is it not tidy because we would need to wrangle it to have 3 columns so that each CO2 observation would have a row? All right, great. So the correct answer here is the fourth one. Each row corresponds to a bunch of different years. So we would need to take all those values in the data frame and put them each into their own row with columns corresponding to the year and month. All right, cool. So let's actually do some R stuff now. So the first package we're going to talk about from the Tidyverse is a package called dplyr. And it's useful for performing a lot of the common data frame manipulation operations that we've already seen how to do using vectorization and base R. So for example, we talked about how to change a data table by adding a new column previously by assigning to that name. So you can do the name of the table, then a $, then the name of the column, and then assign to that a new vector, and that creates a new column. dplyr has a different way of expressing that, which we'll see has some advantages in a little bit, but let's talk about what it looks like first. So we're going to use a function called mutate, and we'll also see after that a function called filter, which is used to select certain rows. So we did that with vectorization before, but we'll do that with the filter function now. And if we want to select specific columns, we'll use the select function. All right, so let's start with the mutate function here and let's see what this looks like. So first of all, we'll load the Tidyverse package, and this is what's called a meta package. It will load many other packages that belong to the Tidyverse. That way, if you want to use several of these packages, you don't have to load each one. You just load the kind of umbrella package, and you'll get all of those packages as well. We're also going to load the DS Labs package so we can have access to this data frame. I think we already did that, but just in case someone missed it. All right, so let's take a stock briefly here of what happened. So it said it's attaching packages, several of them. So ggplot2, that's the graphing one, tibble, whatever that is, tidyr, readr, per, stringr, forcats, and dplyr. So we see that it did load dplyr, and we can start using some of those functions. And it also tells us that the base filter function, or the stats filter function that we would have normally gotten without loading this, it's now going to be giving us this other function. So we should watch out for that. Okay, so but let's look at what happened here. We called the mutate function with murders as the data frame. That's our first argument. So it's going to be a consistent theme. First argument is our data frame. And then we just define a new column here with sort of the minimal code it takes to do this. Notice that there are no $signs or anything here. We're able to say total, and it's going to know that we mean the total column of the murders data frame. Likewise with population, we do this whole vectorized operation here and assign the value that we get, the new vector that we get, to the rate variable, and that's going to appear in the resulting data frame. So there is something fishy going on here. If you're used to other languages, this warrants some explanation. We've talked about this a little bit before, but this is a very special thing about R, and dplyr takes full advantage of it. So when we write total and population here, these are not variables which are defined in our workspace. So in another language, this would necessarily throw an error, and it would say, I don't know what these variables are. And if you wanted to do something like this, you might have to put them in quotes to make them strings or something. But then that would be kind of weird because you'd be dividing strings, which doesn't really make sense. So what R is doing here is actually looking at your code. It knows that the second argument of the mutate function is something where you might be referencing some of the columns of the data frame directly with their name. So it performs that lookup operation for you, much like the with function that we've already talked about. So the point is that this makes the code tidier. We don't have a lot of $signs. And what we can see, if we just look at the variable murders now, is that we have a new column here called rate, which contains the murder rate. So we did that before again, but this is a little bit cleaner way to do it because we're only expressing our intent. We're using the mutate function, saying we're going to create a new column. We say the name of it, and then we say the formula that we want to generate those values, and that's it. There's no extra stuff that has to happen. With one exception, which I'll note here as there's a question about it from Brett. So when you call the mutate function, perhaps somewhat confusingly, it does not mutate the variable. It creates a new data frame. And that's why here we do have to assign to the variable murders again. So if we just called this line of code by itself, then it would display a data frame with the new column for us, but it would not store it anywhere that we could then begin to use it. And this seems like an annoyance at first because you have to write this extra code, but we're going to learn a trick very shortly that spares us that and explains why it is in fact clearer to use this non-mutating version where it doesn't edit the original variable. So yeah, that's correct. So we've overwritten the original murders object, but it doesn't change the object loaded with data murders. We could load that again, but it changes the variable that's in our session. And we did have to assign that to the object again, because otherwise it would not have changed the original data frame, or it did not change the original data frame. It created a new one, and then we saved that new one. Okay, so let's move on to a second function because we can write some more interesting code if we combine a couple of these functions. So suppose that we want to, let's say, filter the data table to only show states with a murder rate lower than 0.71. So we've done this before again, and what we did before is we used vectorization to come up with an object that stores the indices of the rows that we want to be looking at, all right? And then we index the data frame with that vector. But dplyr gives us a way to express that idea without having to think about the vectorization and indices. We can just say exactly what we want and we get what we want. So we say, starting with the murders data frame, let's filter it. And let's filter it on the condition that the rate variable is less than or equal to 0.71. So you can hardly imagine expressing this operation more succinctly than this. And it does exactly what you want to do. The rate is less than or equal to 0.71 for all of these, and for all the other ones, it's greater than 0.71. Okay, so I want to give you a problem that's a little bit more challenging. Hopefully it's still within reach, but it'll require thinking a little bit. So I want you to try to write a block of R code which returns every other row. So the second, the fourth, the sixth, and so on. And the double % sign is useful here because it gives you the remainder when you divide one integer by another. So see if you can combine some of the ideas that we've developed here to perform this operation. Feel free to ask a question, by the way, if you feel stuck during this time, because I'm happy to respond to you. Okay, so this one was maybe a little hard because no one really got it right. So well, let's work through it together. That's okay. That's good information for me, and I think you'll be very well positioned to understand the solution once we do it together. Okay, so let's start by creating a column that specifies the row index. So if we look at this murders column, this murders data frame, we have no way of saying, based on variables that are actually in the data frame, which ones are even and which ones are odd. So we need to add that information. So what we can do is use the mutate function that we just learned and just add a new row. So I'll just call it row index. You can call it whatever you want. And we'll just do 1 to 51. So now we have this column, and now we can filter on it. So let's call this indexed murders and then filter indexed murders on the condition that the row index value is even. And if you want to say a number is even, that's the same as saying that when you divide it by 2, you get a remainder of 0. And this did exactly what we wanted. We now have, we don't have Alabama, we do have Alaska. And then the third state, which I've forgotten, is skipped. And then we have the fourth state here and so on. So you can see clearly that that worked properly by looking at this row index column that we added in order to obtain this result. Okay, let's move on to the next function, which is select. So this one is a bit simpler. So all you do is call the select function on the data frame, and then subsequent arguments, however many you want of them, are just variable names of columns that you want to grab. So let's say we only want state, region, and rate from the murders data frame. And then maybe let's also filter it. So this operation looks like this: select from the murders data frame these 3 columns, store that as a new variable called new table, and then we can filter that table on the condition that the rate is less than or equal to 0.71. And so we get this smaller data frame. Note that the first object that you call is a data frame, but the next, whatever subsequent variables are variable names from the data frame. Okay, so here's another little exercise. Write some lines of R code to create this table shown in the image loaded here. So that's each state abbreviation along with the state's population in millions. Yeah, so folks need more time. I want to give you more time on this one. If you already answered, that's okay. You can just answer again. I'll give folks another minute. I think maybe 1.5 to 2 minutes is not quite enough time when you're getting used to all of the syntax and stuff here that might be new to a lot of folks. Okay, so let's go ahead and do it together. Make sure we're all on the same page here. So the first thing we need to do is create that population in millions column, which is not there already. And as we just learned, we'll use the mutate function for that to create a data frame that has a new column, pop in millions, which is just going to be, of course, population divided by 1,000,000. So let's see what that looks like. Okay, that's the column that we wanted. And let's just give that a new name for now. Again, we are going to learn a cleaner way of dealing with this part of it. We'll give this a new name. And then we don't want all of these columns. We just want a specific one. So we'll select from state pops, we'll select the ones we wanted, which I've forgotten now. Just abbreviation, and pop in millions. And that's looking pretty good, except it's too long. What was done here to produce something that isn't super long was just to call the head function. So if you call head on a data frame, it just shows you the first few. That part's not so important here. What I really want to focus on is how mutate and select can work together to create new columns and then subset to obtain only particular columns if you want to kind of get rid of some other ones. Yeah, one person said I used filter instead of select, right? So you do have to remember that select is for columns, so you're selecting particular variables, and filter is for rows, so you're filtering out some of the rows. I don't think there's a canonical way to remember which way is which, but you get used to it. Okay, yeah, so just to send for just to send this to everybody in a message as opposed to just having it where I typed it out. Okay, another thing that I'll mention, this isn't in the book, but I'll just mention it briefly because I find that it is pretty handy to know. So sometimes you want to drop 1 or 2 columns, and you don't want to have to come up with a list of every other column that you want to keep in order to do that. You just want to say, drop this one for me, or these 1 or 2. You can do that with the negation operator. So if you put a negative sign directly in front of the name, dplyr recognizes this expression structure and it drops out whichever row you're talking about. So earlier we had indexed murders where we added a column to do an operation on it. And you don't really need that column once the operation is done, or you might not. And you might want to drop it. So select will allow you to do that and just say, hey, drop this one variable. And you can see that it's not there. If you look at indexed murders without the select operation, you're still going to have that row index column over here to the right. Okay, so this operation that we showed here is just dropping that last column. Okay, so here's another little exercise. I'm going to go ahead and add more time to this one right up front. So write some R code which produces a new table containing all the columns in the murder data frame, but only those rows corresponding to states that are not in the West. Okay, so several good answers here. You hopefully recalled that the filter function is the right one, and then it's just a question of getting the correct computation. So to subset the rows of the data frame, we use the filter function, and we just write the condition for subsetting here. So we want the region to be different from West, and different in programming speak is this not equal to operator. So that was, I guess, kind of the main thing to remember here. All right, so if we look down this data frame, we'll see that there are no Wests here, and we have successfully dropped all the rows that correspond to the West region. All right, so let's clean all of this stuff up. This is an important part to do sooner rather than later, because we can start writing nicer code. Okay, let's look at this calculation. So we're taking our murders data frame and adding a pop-in columns, or sorry, pop-in millions column. And then we store that to some variable, which we called state pops. And then let's say we want to choose certain columns. Again, we have to store that to a variable and then compute the, well, just the head of that to present the first few rows here. Okay, so I want to think about what about this is not ideal from like a language design perspective. Oh, a couple of questions came in that I'd like to address about the previous exercise. So the question is, why didn't I assign to a variable here? You certainly could do, and in a script, you would really need to do that. The reason I didn't is I'm taking advantage of the fact that this interactive R environment, when I run a line of code, it will output the result of that expression for me. And all I want to do here is look at it anyway. So if I assign this to a variable, I would have to call that variable on the next line in order to see what's going on. And then if I have no intention of using that variable later, which I don't, then I've just wasted some keystrokes and some space. So yeah, so this is a good point. I couldn't use that later because we didn't assign it to a variable. But we just want to look at it anyway. So this happens a lot when you're doing interactive R computing. You think, oh, I wonder what this data frame looks like when I filter it in a certain way, or produce this new column, or make a graph, and you just write the code to produce exactly what you want, and then you look at it. And then if you want to keep it around, then you can think about the right way to do that. But otherwise, you can, so that might look like assigning it to a variable. You might just save it in a file, or if you're using R to generate a readable report, then you can put it in its own cell to execute and have its output display in that final PDF or HTML report, something like that. But in any case, that's what's going on there. Okay, so yeah, so let's look at this pipe example. Or sorry, this pipe discussion again. So this example kind of warming up to the concept of using pipes. So yeah, so let's think about how we would like to improve this if we're imagining a better user experience as the programmer here. So there's some things that happen are important. That, for example, we specify population in millions in the way that we want. We say which columns that we want. The programming language can't do those things for us. We really do have to express those ideas, because this is what we're saying what we want as the user. But this part of it is not really necessary, or it's only necessary for bookkeeping reasons. Assigning to a variable is not really what we're doing here. It's just there so that we have that computation stashed and can use it on the next line. And the operator that is used in R to solve this problem is the pipe operator, which is a forward arrow surrounded by percent signs. And as you recall, this surrounding by percent signs, that is imposed by the base R language. If you define your own operator, it has to have those percent signs. And this is, you know, it's in a library. So some person decided they wanted this. Unfortunately, I don't remember who created this package. It's called Magritter. But in any case, someone decided they wanted this. They had to use the percent signs in order to introduce their own operator. So you want to think of this as sort of mainly a forward arrow. In any case, here's what it looks like to perform this calculation with pipes instead of in the manner that we just did, assigning to variables. So notice there are no variable assignments here. This is just one continuous stream that has been broken up onto different lines just for visual convenience. This is just really one line of R code. And the way we want to read this is the murders data frame is being piped into the mutate computation. And then the result of that computation is being piped into the select operation. And then the result of that computation is being piped to the head function. So we're able to create these pipelines in a way that is explicitly involving pipes instead of leveraging more language features like variable assignment. Yeah, I agree. This is a nice way to visualize the composition that's going on. In other words, when you read this, it very much suggests, if you think of this as an arrow, we're going to start here and then go here next and then go here next and so on. Yeah, it's very clean. There's a question about a little bit about R semantics. Is the indentation in the code necessary or only for aesthetics? So R does not use what's called semantic indentation. It does not rely on exactly how you indent your code to execute it properly. So yeah, it's only there to look nice. I will say though that you can't put new lines willy-nilly. The arrows do have to go at the end of the line. So if you thought, I don't really like them at the end of the line here, I want to put this here, you can't do that. It will, because what will happen is R will execute this line of code and it sees that it's complete. So it just runs that line of code and then it goes to the next line of code and tries to run that as a complete object or as a complete section of code. And it's not, because it doesn't have the stuff that comes before this operator. So you do have to put the pipes at the end of the line though. If you're going to introduce these new lines. So this is kind of the standard way to do it. All right. So the point is that this is significantly shorter code and it's exactly expressing our intent. So this is a really common theme in the Tidyverse packages. You want to be able to organize your operations in a coherent way and then express your intent for the operations you want to perform as clearly as possible in code without having to bring in extra conceptual baggage like how do various vectorized operators work when you're trying to come up with an index to use to subset your data frame or perform some other operation. Yeah, we have an experienced R user giving us a warning here. Pipe placement, and then when we learn ggplot2, that we'll be using a sum operator to combine objects instead of a pipe, and it's a similar thing. But the common thread is that you need to put the operator at the end so that when R gets here, it's like, okay, murders piped into what? And then, well, I guess I've got to the next line. So that's kind of what the R interpreter is doing. It's seeing that this is incomplete and going to the next line. Then here it sees that this one is incomplete and so on. And so it's sort of forcing R to consume this entire expression at once, even though we used new lines to separate it into this visually discernible way. It looks much worse without the new lines. I mean, especially in this interface, but really in general, this is not how you want to program. right? Being able to use the new lines properly is important. Okay, but we need to explain what's going on, because if you just see this and you don't have any introduction to it, you're really guessing what could possibly be happening here. And it's not terribly complex. At least the basic usage, you'll be able to wrap your mind around pretty quickly. There are some extra features in the Magritter package that are sometimes used in this Tidyverse code, and it'll take you some time to learn all those details. But the basic idea is just that the pipe forwards what's to the left of the pipe to the function on the right as its first argument. And you can have additional arguments or not. So here's a really simple example. Square root is being called here sort of apparently with 0 arguments, but actually it has 1 argument because that argument is being piped in from the left using the pipe operator. So when we pipe 16 into the square root function, that's going to be equivalent to if we just did square root of 16 like that. Right? So we see we get the same thing both ways. And a nice thing about the pipe that you can see even in this form, where we're just using no argument functions, is that you can put them in sequence like this. You can say, okay, well, suppose we start with 16 and then square root it and then take the log. You can do that either way. You can do log 2 of square root of 16, but this puts the computation left to right in the order in which it's actually performed. So that's kind of nice. Now, when it forwards the value, as we said, it only forwards it as the first argument. So if there are more arguments we need to use, we can just include those directly. So we can pipe 16 into the square root function and then pipe that into the function which takes the log of some argument with a base of 2. And we'll get a value of 2 here. So this is, well, it's the same computation because that's what the log 2 function does. But if we wanted to use some more exotic base like 3, then we could do that just fine. Okay, so the important thing is that when you have this pipe operation, this function call is a little bit illusory. It looks like it's only being called with 1 argument, but in fact, it's being called with 2 arguments, the other one coming in the first position from the pipe. All right, and in fact, it's important that you drop the first argument because, of course, if you tried to include the first argument here, then there would be a problem. You'd be piping in an extra argument and it would be messed up. So it's important when you use the pipe that the thing coming from the left is the first argument, and what you might otherwise type for the first argument has to be dropped. Okay, so for example, if we take the murders data frame, we could pipe that into the select function, and now we're only putting the variable names that we want to actually select. We don't have to keep writing some name for the murders data frame. And then that data frame comes out of the resulting data frame coming out of that operation goes into this filter operation, which again only includes the arguments subsequent to the data frame. And this creates this really tidy appearance of our code where you can almost read it like English. We start with the murders data frame, then we select the state, region, and rate columns, and then we filter on the condition that the rate is less than or equal to 0.71. So we don't even here have to think about how the first argument is an object and the subsequent arguments are either variable names or in this case a vector. It just happens for us because that first argument is coming in from the left. Okay, so there are a few questions here. Are there performance concerns? Not really. I mean, there are performance concerns in general with R, but not any special ones associated with this particular type of operation. It's going to do these things in a vectorized way if you write them in a vectorized way. So there's not really any considerable overhead here. So I think this question must have been from earlier. It only works when there's 1 object to operate. No, you can. Oh, I see. This is more subtle than I was thinking. Yes, what we've learned so far only allows us to pipe 1 thing at a time. So you can take 1 value from the previous line and pipe it into the next function. However, usually what you would do to deal with multiple values of interest that you might want to be piping along is to combine them into a single data frame. So if you have extra variables you're interested in, you can put those variables, assuming they fit into the framework, you can put those variables as extra in your data frame and you'll be fine. Yeah, if you're familiar with SQL syntax of structured query language, which is a standard way of accessing data from a relational database, then yeah, it is similar to that. And in fact, there are some tools for kind of interfacing between the dplyr way of doing things and the SQL way of doing things. Okay, one more questions that I've gotten, all of the questions that came in that cluster. Why don't we need a pipe after filter? That's because the last line is, so this whole expression, the way it works is that this value goes into this function and this value goes into this function, and then there's no more pipe, so we're done. So we have this whole operation representing this composition of two operations. And this whole entire expression returns a data frame, whatever the output is. We then have to do something with that. Either we just display it, which is what happened here. So the Jupyter cells allow us to conveniently display the output of any expression just by writing the expression. We don't have to do anything special to get it to display. Or we might have to assign it to a variable name. So, you know, that would look something like this. You could do that. But in any case, we certainly couldn't have a pipe all the way at the end and nothing else, because then R would be like, okay, well, what are you piping this into? It'd be like, what's next? I don't see anything. And it would have it doesn't know what to do. It's going to give you an error, unexpected end of input. It's like, this is an operator, nothing's coming next. And it's supposed to be, you need to fix that. All right, so this is what it should look like. Okay, so one point here is that it's kind of important if you're going to use this pipe function with a package that's handling data, that the data be the first argument, because you want to be able to conveniently say, okay, I manipulate the data frame in whatever way, then pipe that out to the next function and it's going to manipulate it in some other way. The data is what's undergoing these transformations. And because the pipe by default inserts in the first position, you need the functions to take data in that first position for it to be convenient. And of course, the Tidyverse packages do exactly that. Okay, so I'm again going to increase the time here. This one is maybe a little challenging. You know what? I'm going to increase it even more. So this is a little bit of practice with this new syntax. As well as introducing a new function called starts with, which allows you to perform the filtering operation being requested here. So the prompt is to return a data frame containing the state names that start with the letter M. So last time we mentioned there's several of them. Let's say you want to know exactly how many. So we'll filter on that condition. And let's say we also want to know the state's murder rate rank. So we talked about the rank function previously. So write some R code that will perform that operation for you. So Griffin asked a good question about starts with. This is how it works. Starts with, and then some vector, and then whatever string you want to check, whether it's at the beginning of the vector. Or sorry, at the beginning of each string in the vector. All right, so we have, I guess, one answer here with a lot of the key pieces. So here's another one. So let's take a look at some of these. So okay, so here we have the murders data frame, and we pipe it into the mutate function to create a rate column, which we've done before. That looks great. And then we filter with the starts with function. That looks great too. So the only thing missing here is just the rank, but this does the kind of the other operations perfectly. And this one does, so this is interesting. This one's a little bit different. So here we pipe the murders data frame into the filter function first and then compute the rank. All right, and the rank is going to be different after you filter out the ones that don't start with M, because your ranks are just going to be 1 through 8 instead of 1 through 51. So there's a different operation, but this does include the rank here. So yeah, let's walk through this together to make sure kind of all on the same page with this operation. I think this one was there's kind of a lot going on. You know, I want to make these exercises a little bit interesting so that you don't feel like you're just sort of changing variable names. But yet when they get pretty interesting, they get hard to do in a minute or two. Okay, in any case, so the first thing we're going to do is mutate to add a rate column like we've seen before. And then here's a nice trick. So what I was expecting people to do is to pipe again and create a rank column like this. And that's completely fine. So we create this new column that we want to find the rank of, and then we call rank on that column and store that as a new column. That works. You can also contract to mutate operations like this. And you would think that wouldn't work because rate was just now defined here in this first argument, but R is magic in that way. It can actually go through and add this one first and then add this one second. So that would not be possible in another function, in another language, because both function arguments would have to be evaluated before the function is called, but not in R. R can look at your code, so it can go ahead and execute this part of the operation and then execute this part next. So let's do that in that slightly tidier way. And then we said we want to select just the state and the rank. So let's do that. We could do that later, but just do it now. Select just those two columns, and then pipe that to the filter function, which is what we're going to do to subset the rows. So just like we said, we can do starts with and pull out the state column, and then for each element in that vector, we want to check whether it starts with the letter M. And this should work. And notice I didn't really need to multiply by 1,000,000 here because I'm going to end up dropping that column anyway. It doesn't matter whether the scale factor is nice. So let's just do it like this. As we see that these are our M states. Some are close to the top and others are close to the bottom in terms of the murder rate. But this is the operation we wanted to perform. And again, you can see that it's performed quite succinctly. We start with our data, and then we just say for each line here, we say exactly what operation we want to perform, nothing more, nothing less. Okay, and then my final comment for the day is that you might be tempted to check whether a string starts with the letter M by indexing it in its first position and comparing that to M. This is what I think people coming from other languages would be inclined to do. However, that doesn't work because the operation is not vectorized. So state brackets 1 returns the first element of the state vector, not the first letter of the character string in each element of that vector. So this is an issue of relying heavily on vectorization, as R does. You really need to know about this special vectorized function starts with in order to do this in an efficient way. Implementing it yourself requires a little more boilerplate and has some performance penalties, or you could just make a mistake and write some code like this that actually just doesn't work. Oh, thanks. Yeah, Tom is paying close attention. I made a mistake up here. I said population over total. Used to the word total being the denominator when you compute a rate, but total here is the murders, so it should be total over population. So yeah, thanks. You're definitely right about that. Thanks for dropping in, and I hope you've enjoyed this section. We're going to pick up with the Tidyverse next time.